like this, and then I've got one more kind of analytical problem example we can do if you want to, okay? So the following figure gives the graph of the derivative. You got to make sure you read these carefully, because what mistake do you think people make on this one a lot of times? They say it again? Yeah, they treat it like the function instead of the derivative function, right? So this is the derivative. Sketch a graph of f on the same set of axes. Okay, so you got to just think about this kind of like in terms of the table, right? Where would the critical numbers be? -1 and -3. How come? Keep in mind this is the derivative function, because that's where the derivative is equal to 0, right? So these would be the critical numbers. There and there. So if there are any extrema, they would have to exist only at those two places. Okay, what's going on at -3? What kind of an extremum is that? It goes from negative to positive, the derivative. So it's going from, what's that going to look like then? It's going to be a minimum, decreasing to increasing, right? Because look at the sign of the derivative here. It's negative every place here. So that's going to be an interval where it's decreasing. This is going to be an increasing interval where the derivative is positive. And then all this stuff over here is going to be another decreasing interval. So it would have to look, it would have to be a minimum there, wouldn't it? We know we're going to get a minimum there. What's this one going to be? It's got to be a maximum, doesn't it? Because look, it's going from increasing to decreasing. So it's got to be like that. So then what does this thing really have to look like? It's got to look something like that, doesn't it? Right? You get the idea? And do you know exactly what it looks like? No. I mean, we haven't really discussed enough. We haven't talked about the second derivative and concavity. So you can't really make, at this point, a super detailed sketch of what's going on. But that's really not the point, right? You just have to pick one of the options that would be suitable, that would match. Okay? Does that make sense? Okay. How about this? The following figure gives the graph of the derivative, again, of a continuous function, passes through the origin. Sketch a graph of f on the same set of x. Okay, well, what's going on here? Where are the critical numbers on this one? -2, +1? Yeah, okay. So -2, +1. Those are the places where we would have to have, if extrema exist, that's where they would have to exist. What's going on at +1? It's going to be a minimum, isn't it? It goes from decreasing to increasing, right? Negative derivative to positive derivative. So it's got to be something like that. What's going on at 2? It's got to be inflection, doesn't it? It goes from decreasing to decreasing, right? So what's that look like? And it does have a 0 derivative, so it has a horizontal tangent, right? We know it's got a horizontal tangent, but it's doing this. It's going from decreasing to decreasing, so it's got to do something like that, doesn't it? Everybody see how that works? So if I were to connect these in a way that made sense, it would just look something like, well, we know it goes through the origin, so it has to go through that point. So I guess it would have to do something like that, and then over here, it would just have to go, something like that, right? Basically. I mean, is that the exact shape? Probably not, but that's, essentially what it's got to look like. Okay, give me 1 to 5. Is that all making sense? Okay. Questions? Okay. Probably just need some practice on this. Okay, so again, we're given the derivative function. We're supposed to estimate the intervals on which the function is increasing, decreasing, and the x coordinates, can't really provide y coordinates, but the x coordinates of all local extreme values. And let's tell what kind of extrema they are. Okay, well, this one is, I mean, really, we've already done all this stuff. Where would it be increasing? Well, but this is a graph of the derivative function. It's a graph of f prime again, right? No, you're mistaking this as a graph of f. So where is it increasing? So let's, how about if we like color code this, right? So increasing will make red or blue, I guess. So what part of the graph of the derivative would correspond to an increasing function where the derivative is what? Yeah, positive, right? So where it's above the x-axis. So this part right here would be a part where the function's increasing. This part right here would be a part where it's increasing, and that's it, right? So it's increasing on, using interval notation, what would that look like? Negative infinity to 0, bracket or parentheses? Parentheses, right? Because it's not increasing at 0. At 0, the derivative is 0, right? Or 2 to 3. Okay, now where is it decreasing? Well, any place where the derivative function is negative, so where the graph is below the x-axis. So it would be here and there, right? So 1 to 2, or what? 3 to infinity. Okay. Estimate the x coordinates of all local extreme values. Okay, so what's going on here? Oops. What's going on here? We're going from increasing to decreasing. Question? Yep. Did I do? Oh, you're right. 0 to 2. Yep, you're right. There you go. Yep. And at x equals 0, we have a relative maximum, right? And what's going on there? Oops. X equals 2, we have relative minimum, right? We're going from decreasing to increasing. And also at where what's going to happen at 3? Maximum. Okay, so we'll just add We'll just add 0 and 3 as the places where we have relative maxima. Okay? Okay, this one, really, what's the only part on this one that's different than what we've already done? At what x value? -2, right? At -2, something weird is happening, right? What's happening at -2? This is the derivative function. Well, actually, no, nothing weird is happening. That's not true. Mm-mm. It's because this is the derivative graph. And so let's talk about -2. I mean, it looks like something weird is happening, but let's discuss that. Okay, does the derivative exist at -2? It does, right? Why might you say no? Right. Okay, because it's a sharp corner, right? But the derivative doesn't exist at a sharp corner for the function. See the difference, right? In this case, if the derivative didn't exist, what would have to be on the graph? We'd have to have a discontinuity in the function, right? Does that make sense? Or it'd have to be some kind of an asymptote or something. So the derivative, what is the value of the derivative at -2? It's, I don't know, it looks like it's -15. Okay. That makes sense? Okay. So find the locations of relative extrema. So what are we, I mean, where are the places where we get relative extrema here? Yeah, we're getting relative extrema here, 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 and there. The places where the derivative is equal to 0. Is the derivative undefined anywhere? No, right? If the graph of the derivative is continuous, then the derivative is nowhere undefined, right? What's it mean for a function to be undefined? For a function to be undefined, it means it's not defined at a place. You can't graph it there, right? As long as I can graph it every place on that interval, it's defined everywhere, okay? So real quick, I mean, we've done this probably more than we need to. What's this one? I always just think of it in terms of like, what are you doing? Like increasing to decreasing just makes a peak, right? Decreasing to increasing would look like that. Increasing to decreasing, decreasing to increasing. So, right? Okay. That makes sense? Questions on that one? Yes. So what would that look like on the graph? Okay, so if we were going to graph this thing, this part right here, what's going on there? All that's happening is the curve is getting steeper and steeper and steeper in the negative direction, and then it reverses that process. So this part right here would just look something like this. The curve is getting steeper and steeper and steeper and steeper, and now it's starting to level off a little bit like that. See what I'm saying? That's not supposed to be vertical. It's just steep. You get what I'm saying? And then when it gets up to here, that's where it's going to flip over and start to become positive. Okay? Does that make sense? Okay. All right. Okay, now this is the one I was kind of wanting to get to. Okay, a lot of this we've already done, but on this one, what's something that's different that we haven't yet talked about? This is the derivative function. At what x value do we kind of investigate a little bit? At 4, right? What's going on at 4? There's a discontinuity in the derivative. The derivative is undefined, isn't it? Right? It's undefined at 4. So what's happening there? We're going from, what's that going to look like? It's going to be, I'm going from increasing to decreasing. So that sounds like a peak. It's going to be a sharp peak because we're instantly going from a a relatively large positive slope. So it's going from increasing to a relatively large negative slope. So it's doing something like that, isn't it? You see that? Okay. Assume the function is continuous. So that makes sense? And then the rest of it's pretty straightforward. This is just going to be, this guy right here is going to be decreasing to increasing. So that's just going to be a place where I guess we would do this though, wouldn't we? We're going to be, it's going to end there. But you get the idea. Oops. What I wanted. That's what I wanted. And then what's going on here? This is going from decreasing to increasing, right? So that's going to be a minimum. So it's going to do something like that. I mean, this, again, that's pretty bad crap, but you get the idea. And here it's doing the opposite. I got to fix that. That looks terrible. And then over here, oops, it's doing something like that, right? That's supposed to, oh man, that's so bad. Not much of an artist, am I? That's terrible again. I can't seem to get that. So there's my minimum, and my maximum's got to be there. There. Okay, you get the idea, right? Jeez. Yeah. Yeah. Uh-huh. Yeah. Okay, what about this? Now this is kind of a cool one. So we want to come up with, we want to fit this cubic function given this information. Okay, what are they telling us? They're telling us we have a local maximum at the point 0, 0 and a local minimum at the point 1, -8. That's a lot of unknowns to solve for though, right? If I've got 4 unknowns, how many equations do I need to solve for 4 unknowns? I need 4, right? I need at least as many unique equations as I have unknowns to solve a system. Okay? So where am I going to get some? This is the function is a polynomial. So where am I going to get some equations to solve that I can use to solve for, A, B, C, and D? Okay, we could find the derivative, right? So if that's f of x, what is f prime of x? X squared, right? Plus 2bx plus c. Okay. What do you know? We could, not gonna do us any good. Okay, where and why? Critical points. We have extrema, right? The only way that can happen is at a critical number where the derivative is continuous or undefined. But this is a polynomial, so is the derivative ever undefined? No. Okay, so we know that at this point right here, this is a local maximum is at this point, right? So when x is 0, what has to be true for the derivative? Has to be 0, right? So we know that f prime of 0 would equal 3a times 0 squared, right? Plus 2b times 0 plus c, and that is equal to 0 because the derivative at this point at x equals 0 must equal 0. It has to be a critical number, right? Okay, so that's kind of good. Look, it tells us one value right away. Okay. What about this local minimum? What's that tell us? If a local minimum occurs at the point 1, -8, what is f prime of 1? If it's a local minimum, it's got to be a 0 derivative, doesn't it? You see what I'm saying? So f prime of 1 has to equal 0, right? Well, what is f prime of 1? F prime of 1 is just going to be 3a plus 2b times 1 plus c, and that's equal to 1. Okay, so we get another, there's another equation. We got two equations. Okay, where are we going to get the other two? We need two more equations. So we need some specific information, I guess, right? Okay, because we were told where there were extrema, we knew the value of the derivative at two different x values. Do we know anything else? What do you think? Yeah, the value of the function. Give me an example. Oh, okay. So at x equals 1, the function has a value of -8. At x equals 0, what's the value of the function? 0, right? So if we take this point right here, that's a point on our curve, right? So what's that telling us? That's telling us f of 0 equals 0, right? And maybe this would be helpful if I wrote, like, next to this, this is really just saying f prime of 0 equals 0, right? That's what we did there. What did we do with the green one? Well, we just said f prime of 1 equals 0. That gave us that equation. Okay. The blue point is just telling us f of 0 equals 0. Okay, so what's that tell us? Well, there's f of x. So f of 0 is 0 plus 0 plus 0 plus d, right? So d equals 0. Right? And then the last one is this other point at 1, -8. What's that tell us? F of 1 equals -8, right? So f of 1 would equal times 1. So a plus b plus c plus d equals -8. Well, there's my system of 4 equations and 4 unknowns. Now, this is a pretty easy system because we already know what c and d are, right? So then we could take the green equation and the orange equation, and that's going to collapse into just a simple 2x2 system, right? What's the green equation going to become if we plug in the values of c and d? They're both 0. So I'm just going to get 3a plus 2B equals 1, the orange equation, when I plug in values for C and D, becomes A plus B equals -8. You can solve that any way you want to, substitution, or probably just we'll use elimination, I bet, huh? So if we were just to multiply, or just leave that one alone, multiply that equation, distribute a -2 through, we'd get 3A plus 2B equals +1. Down here we'd get -2A minus 2B equals +8. Add those up. We eliminate the B's. Remember doing this stuff, right? Oh, 16. You're right. 16. Yep. Remember doing this stuff, right? And we're just solving a linear system. So that's going to give us A equals 17. Okay, so we know another one. Oh, how'd we get 16? What the heck? What's that? What the heck? That's impossible. 3A plus 2B plus C. Okay. We didn't get D. Well, D's, that's right. So then A plus B plus C plus D equals -8. Those go away. What's that? Yeah. I think, boy, I think they're wrong on this. I really do. A equals 17. I think that's right. We can easily just graph these things and see, right? When we're all done, we'll just graph them and see. And if A is 17, then we could just go back. B would have to be what? So then B 17 plus B equals -8. So B would equal -25. What is going on? Oh, I know what it was. Yeah. What's f prime of 1 equal to? Duh. 0. Not 1. Right here. Right? There's the mistake. Right? That's supposed to be a 0. So down in this equation, that's supposed to be a 0. So that's a 0. So that's a 16. And that's a 16. And that's a -24. That's what we wanted, right? There we go. Okay. This is the last one I kind of thought maybe it would be worth looking at. Let's at least just talk about it, and you can decide if you want to do it. So the electric power P in watts in a direct current circuit with two resistors, R1 and R2, connected in series is given by this expression, okay? Where V is the voltage, and obviously R1 and R2 are the resistance of the two resistors. So if the voltage and R1 are held constant, what resistance R2 produces maximum power, okay, in this circuit? So what would we do? These kind of, the reason I picked these kind are always, they just visually, people just get confused by these. What's the only variable here? R2, right? So everything else is just a constant. And so when we differentiate, we'll treat those as constants, right? So really, we just need to differentiate. And this is not a horrible derivative. I mean, it's not the best in the world, but it's not a horrible derivative. If I differentiate this guy and get P prime, how am I going to have to differentiate that? I could use product rule. I don't want to rewrite it though. So let's just use quotient rule. Okay. Right. Because what are the variables? The variables, look, I've got an R2 there and I've got an R2 there. Everything else is a constant, right? So if we apply the quotient rule, this is good practice, what are we going to get? What's quotient rule? Low D high minus high D low. Okay, so low is going to give us R1 plus R2 squared. D high is what? VR1. Everybody see that? Okay. Minus high D low. Yikes, what's D low? Okay, 2 times R1 plus R2 times 1, right? All divided by R1 plus R2 to the fourth, right? You got to square the bottom. Okay, so if we clean that up a little bit, what's that going to give us for our derivative then? We're going to get P prime equals, if I distribute here, distribute the VR1, oh no, it's not that. I got to FOIL that. Let's factor out. No, you guys talk to me. You tell me what to do. What am I going to do on top? What could I factor out? I could factor out a VR1 and also R1 plus R2. Everybody see that? Okay, so I could factor out a VR1 times R1 plus. Now I'm just going to color code every place where we have the variable. I'm going to make that a different color so it stands out, right? We factored that out. What's left behind? Okay, we're left with R1 plus R2 minus 2R2, right? Everybody see that? Okay, divided by R1 plus R2 to the fourth. So we could cancel one of those factors, right? We could do this. We could cancel that guy and make that cubed. And then if we clean that up, we get P prime equals this constant, which we don't really care about, VR1 times, what's this all going to be? R1 minus R2. Okay, so there's our derivative. Okay, so something we haven't really done yet. We're going to do more and more of this as we get into optimization stuff. Any questions on that? Does that all make sense? Okay, what's confusing about it, I bet, is all the ones and twos and right. You gotta be just concentrate on the fact when you're doing these that R2 is the variable, but it looks just like it doesn't really look like a variable compared to the other ones, but we know it is because that's what we're told. So the other stuff we just treat as constants. Okay, what would the domain be of R2? What are the valid input values for R2? Because this is not just a math problem. This is a physics problem. What's the? You guys probably don't know a lot about resistors, I bet, at this point. But a resistor is just a circuit element. The resistance is a measurement of how hard it is to push current through the circuit or through the little resistor, right? If you push current through the resistor, it heats up and it dissipates power. Okay. What's the lowest possible value for resistance? Could it be negative? If you guys can figure out a way to make it negative, see me first and we'll go into business together. Okay, that would be a pretty good deal. So the resistance, the domain here would be, and including zero is even a little bit iffy, but we'll just say zero resistance. So 0 to infinity would be our domain. Okay, because resistance can only be positive. So what would be our critical numbers then? Where is this derivative undefined? Negative R1, but it can't be negative, right? R1 has to be positive because it's a resistance, and R2 can't be negative. So is that really a critical number? It's not, because it's not in the domain of our function, right? Resistance is non-negative. So there's no place where the derivative is undefined, okay? Okay, where is it equal to 0? Okay. P prime equals 0 when R2 equals R1, right? Okay, makes sense? Well, because look, the top's going to go to 0, okay? And so what's happening with our table then? Oops. Let's scoot this guy up here. Okay, so then we've got our values of R2. That's our variable. And that's going to go from 0 to infinity. We've got the power and the derivative of power. We had one critical number at R2 equals R1, whatever that is, some positive number, where the power is equal to 0. Or the derivative of the power is equal to 0. So what do we have to do here to know what kind of animal we have going on there at that critical number? R1 and R2 are both positive. So everything's positive, right? So what would happen for values greater than R1? If R2 is greater than R1, what sign would the derivative have? It'd be negative, wouldn't it? Because then I'd get a negative value from that. Everybody see that? So up here, we know we're going to get negative derivatives. For values of R1, of R2 less than R1, that difference is going to be positive. And so what do we got? That's a maximum, isn't it? We know we have a horizontal tangent and it's a maximum. How about that? That's pretty cool that we can do that, right? We don't even know any values, just a bunch of constants, but we can still figure it out. Okay? So we have a maximum, I guess. R2 equals R1 produces a maximum for power. I'll just write that down for our notes. Okay. Good? All right.